Welcome to This Explainer. Today, we're uncovering an absolutely wild, high-stakes survival story. It's the story of a rocket engine battling its absolute worst enemy, its own extreme heat. When we look up at a launch, we see that spectacular fire. We feel that earth-shaking rumble in our chests. But we rarely stop to think about the phenomenal physics happening right there, inside the metal. So we're going to dive right into one of the greatest, most intense balancing acts in all of aerospace engineering.
Okay, let's just start with this massive number, 3,600 Kelvin. Just to put that kind of inferno into perspective for you, that is over 6,000 degrees Fahrenheit. We are talking about temperatures hot enough to easily melt steel. It's roughly half the surface temperature of the sun. This is a continuous, raging fire that fundamentally wants to turn the engine itself into a puddle of liquid slag.
So that naturally leads us to the ultimate million-dollar question, right? If the heat is that incredibly intense, how on earth does the engine survive without just destroying itself? How do you contain a fire that burns hotter than your own melting point without the whole thing failing before it even clears the launch pad? That paradox is exactly what we are going to solve today.
Here is our flight plan for This Explainer. We'll look at the 3,600-degree problem, then the physics of heat, 5 ways to stay cool, choosing the right system, and finally, the key to reusability.
All right, part 1, the 3,600-degree problem, the catastrophic threat.
Because look, without adequate cooling, all that heat isn't just some minor inconvenience, it is a deadly antagonist. We're not talking about a slight dip in performance here. Uncontrolled heat will literally melt engine components. It causes severe thermal stresses, physically deforming the metal. All this rapid heating leads directly to material fatigue, cracking, and ultimately a complete and total loss of structural strength. Without a way to cool it down, the extreme pressure of those combustion gases would simply tear the weakened melting chamber completely apart.
Moving right along to part 2, the physics of heat, defining the enemy. So to fight the enemy, we have to understand it. The biggest culprit here is convection. Picture this. In a rocket engine, you have these high-velocity combustion gases rushing out to create thrust. Because those gases are moving at supersonic speeds, convection basically acts as a relentless supersonic blowtorch. It is transferring massive amounts of thermal energy directly into the inner surface of the combustion chamber and the nozzle. It is the dominant threat. But convection doesn't work alone. The engine also has to survive heat conduction, which is the heat physically moving right through the solid chamber and nozzle walls. And how bad that is depends heavily on the material's thermal conductivity and its thickness. And then there is radiation. Those extreme high-temperature combustion gases are constantly emitting intense thermal radiation toward the chamber walls. Now, normally, radiation contributes less heat transfer than our supersonic convection, but when you are dealing with temperatures exceeding 3,000 Kelvin, yeah, it becomes a very significant threat.
So, how do we fight back? Part 3, 5 ways to stay cool, the engineering arsenal.
Engineers actually have 5 distinct weapons in their arsenal to defeat the heat. First, there's regenerative cooling, where liquid propellant absorbs the heat before it even combusts. Next is film cooling, which creates a protective layer right on the wall itself. Then we have ablative cooling. This uses a sacrificial solid material that literally chars away. Radiative cooling simply dissipates the heat out into the vacuum of space. And finally, dump cooling, where a coolant absorbs the heat and is just tossed overboard. What's really fascinating here is the dramatic contrast between 2 of these major methods. Take regenerative cooling. It is the absolute gold standard for liquid engines. It constantly circulates liquid propellant to cool the engine while simultaneously preheating that same fuel. It's highly efficient, and honestly, it's the key to making engines reusable. Contrast that with ablative cooling. This one is visceral. It's a sacrificial system. It relies on a special heat-resistant lining that intentionally vaporizes, erodes, and chars away during operation just to protect the structure underneath. It's simple, it's lightweight, but because you are physically consuming the components, it's strictly a one-and-done deal for single-use missions. Now, I want to zero in on regenerative cooling because it builds into what I like to call the regenerative judo move. It's an absolute stroke of engineering genius. Step 1. The liquid propellant is continuously circulated through these tiny cooling channels that completely surround the hot combustion chamber. Step 2. As it flows, that propellant acts like a sponge, absorbing that deadly heat and safely cooling the engine walls. But here is the kicker in Step 3. The now preheated propellant is injected right into the combustion chamber. By using the engine's own dangerous waste heat to warm up the fuel before it burns, engineers actually increase the overall combustion performance.
It's a bit like drinking your own sweat to stay cool while running a marathon, but, much more sanitary and way more explosive. You are quite literally using the heat's own strength against it. And the crazy thing is, engineers don't stop there. They will very often pair those regenerative systems with film cooling. This involves injecting a thin layer of relatively cool propellant right along the inner wall of the combustion chamber and the nozzle. This creates an active, protective thermal barrier. It physically prevents those disastrously hot combustion gases from ever making direct contact with the engine wall. Sure, it increases propellant consumption slightly, and it lowers propulsion efficiency just a tiny bit, but the protection it offers, especially around the super vulnerable nozzle throat, is just unmatched.
Next up, part 4, choosing the right system, strategic engineering.
So how do they pick? The strategy ultimately depends on a really complex web of mission variables. It's like a giant puzzle. Engineers have to balance combustion temperature and chamber pressure, because higher chamber pressure equals a significantly higher rate of heat transfer to those walls. They have to consider the propellant type. For example, cryogenic propellants like liquid hydrogen are intensely cold and they have a massive heat absorption capacity. That makes them phenomenal for regenerative cooling. They also have to factor in mission duration. A long-duration mission absolutely requires a sustainable system, whereas a quick, short burst might just get away with an ablative shield. And finally, material properties play a huge role. You need metals with high thermal conductivity, sky-high melting points, and excellent thermal fatigue resistance. Which brings us to part 5, the key to reusability, winning the thermal war. Ultimately, it all comes down to this core idea. Modern, reusable launch vehicles rely heavily on advanced regenerative and film cooling techniques to withstand repeated thermal loading. And this right here is why this topic matters so much to us today. This booming era of commercial spaceflight, seeing rockets launch, land vertically, and launch again a few weeks later, is only physically possible because we mastered these exact thermal cooling techniques. If we hadn't figured out how to protect the structural integrity of the combustion chamber from basically melting itself into slag, the reusable launch vehicles making headlines right now would be nothing more than science fiction. And that leaves us with one final thought. As we push deep space propulsion to its absolute limits, aiming for Mars and way beyond, what new extreme thermal innovations are engineers going to have to develop next to conquer the heat? It's a provocative question, isn't it? The next frontier of extreme engineering is waiting, and for sure, the battle against the heat is only going to get hotter. Thank you so much for joining me for this explainer. Keep your curiosity burning, and I'll see you next time.